thank you all for coming after lunch. I know it's kind of hard. I'm going to first start with, whenever I give a talk, I kind of ask myself, why should I give a talk? What's my qualification for doing it? And why should anybody spend the real time listening to me? So here's my justification. This issue of the ozone layer depletion and the Montreal Protocol, this all happened in my scientific lifetime. I started working with this as a postdoc, and then I watched this, so I can hopefully tell you a story that's of some interest. I am not going to delve into the details of either the atmospheric physics or the chemistry, but I'm going to tell you a story that you can hopefully relate to. This also reminds me to tell you two other things. I am going to just say things without specifically noting all my colleagues who did some of the work that I'm going to talk about. And also, I want to thank Studium, which have allowed me to come here for a few years in the summer. And in particular, I want to thank my hosts, ICAR, which is CNRS, and in particular, Wahid Maluki, who made me come here. So, here we go. So I'm going to start with a very brief history of the ozone layer. Probably all of you know there's an ozone layer, assume, I hope. It started as being a curiosity-driven science, like most of the environmental science. And then it became a societal issue. I'll kind of walk you through this. And you probably know about the Montreal Protocol and how it came. I'll tell you how it came about. And I'll describe to you the current state of the ozone layer. And there are some unfinished businesses I'll just very briefly touch upon. But in the back of your mind, you're probably wondering, what has this got to do perhaps with things that we think are big issues, such as climate change? Okay? So that's the goal of this for a very short talk. There are environmental issues that are visible. You can see them, feel them, touch them, smell them. Those are things people can relate to. Things, for example, like pesticides, which was heightened by Rachel Carlson's book, which essentially awakened the world to how humans can really do things to our environment. It's actually, if you haven't read it, it's a really inspiring book. Incidentally, Rachel Carlson also kind of was a follower of Jacques Cousteau, who's another pioneer in this whole thing. I'm not going to mention Jacques Cousteau because he did mostly ocean stuff. I'm stuck in the atmosphere. Okay. Then about acid precipitation. This is, people think it's done, but it's kind of going on to some extent. Air quality is something that we're all living with. These are things that you can see. You can actually feel it. So you can actually see these visible human-caused environmental issues. And what happens in that particular case is that the cause and effects are easily linked. Then if you do something about it, you can actually see a change that occurs. So that's the feedback. So if I stop emitting something, if I can improve my air quality, if I can see it, which we did, for example, Los Angeles used to be a terrible place, but it's not so bad anymore. Denver, where I live, also used to have very bad air pollution. But this is reversible, at least on a time scale people can relate to. Within a decade, maybe a generation, upon action, something happens. Now, what about an environmental issue that you can't see? Okay? You can't feel it. So, for example, climate change is something we know is an existential issue. But for a common person, this is really kind of strange when you think about it. When you talk about 1 degree temperature change, people are used to temperature changes of 20 degrees in a day. So you're like, what does it mean? We can talk about it, but the key thing to remember is the human civilization as we know it has developed during the Holocene. Okay, that's the last 10,000 roughly years where the temperature of the Earth has been constant to within about 0.2 degrees centigrade. Entire human civilization has happened during that time. But now we all of a sudden see, since, for example, 1850 to 1900 as a baseline, a temperature change of roughly 1.2 degrees centigrade. That has a huge ramification. Then there's even more kind of bizarre thing. There's the whole idea of ozone layer, which is way up in the stratosphere, which is roughly 15 to 30 kilometers above us. And if you deplete that ozone layer, what would happen is essentially you'd increase the UV radiation, which then causes problems. This is kind of epitomized by the ozone hole, which people always equate with the ozone layer. But one could say, wait a minute, that's happening in Antarctica. What about here? We'll touch upon that very briefly. So these two major environmental issues of the 20th and 21st century are something that you can't quite relate to so easily, unlike air quality or acid rain. And how to get our society to respond to these environmental issues is an interesting question. Now, I'm going to just do a little deep dive into the ozone layer depletion, just a closer look. I just want to just very briefly mention that ozone layer science started being a curiosity-driven science. First of all, ozone itself was discovered about in 1836 by a guy named Schonbein. And then it was discovered in the atmosphere. Incidentally, a lot of our science started from observing the atmosphere. This is one of them. By using a spectroscopic method, you could see there's ozone in the stratosphere. And it was less than 100 years ago that Sidney Chapman explained how the ozone layer comes about. It is simply that the oxygen in the atmosphere can be broken apart and made into ozone, and then it forms a dynamic balance so that you actually have a certain amount of ozone. And the reason you worry about ozone is what happens to it. This whole thing started with a few things. One, with the supersonic transport, which was supposed to be happening very often, that would provide nitric oxide into the stratosphere and that could destroy the ozone layer. Then came this space shuttle. This morning, our astronaut friend talked about this, and the stuff you saw, this beautiful boom and all the thing that came out, that actually has ammonium perchlorate being burnt. And that leaves chlorine. And people thought, at least America thought, would have one space shuttle launch per week originally. That didn't happen for economic reasons, both the supersonic transport and the space shuttle. Then came this thing of this innocuous thing called chlorofluorocarbons that was in hairsprays, refrigeration, air conditioners, and everything like that. And that essentially was what Sherry Rowland and Mario Molina hypothesized. And it used to be that we calculated how much ozone would be depleted, and that is shown in the picture on the right. You see what we thought in the 70s and early 80s was if you keep putting these CFCs at the rate we were putting in 1974, by 2050, that's for 30 years from now, you would actually have a depletion of ozone layer of maybe 5–10%. Okay? So the idea was, this is in the future, it is not big. But then the other question that really important for us to think about, how can small amounts of these really destroy ozone layer? The crux of the issue is it is a catalytic cycle. In other words, a very small amount of these compounds can destroy thousands and hundreds of thousands or maybe a million molecules of ozone. So even if you put very tiny concentrations of CFCs, you destroy a lot of the ozone layer. The reason you became a big issue is, what does that do? What does the depletion of the ozone layer do? I just want you to imagine, if I were to take all the ozone that is in the atmosphere and brought it down to this room, that ozone layer will be about this thick, like shown on this picture, a few millimeters thick. But that is what prevents us from getting fried. Okay, that's the UV shield that protects the Earth from the Earth's surface, the life as we know it. The thing that, of course, caught the big imagination is the word cancer, because UV radiation enhancement causes skin cancer. It also causes cataracts. It also really disrupts the food system because it destroys things like krill, which is at the bottom of the food chain for the ocean stuff, seafood, etc., and plants. As you can see, one plant is radiated with UV, one not. It really has a huge effect on the crop yield and all the things that go with it. So people knew that destroying the ozone layer or depleting it is going to cause major problems to the Earth system. And this is what we're thinking is going to happen in the future. The thing that happened all of a sudden was in 1985. There was a paper from British Antarctic Survey, which essentially showed that the ozone depletion is occurring now, and it is large. There's the ozone hole over Antarctica. You can see this really doesn't tell you how much, but you can actually look at this and figure out how much. This is a depletion of 30 to 40% of ozone over Antarctica. Incidentally, for those of you who might not have been to Antarctica, that's a huge continent. If you take all of the US and put it there, it will be in the middle there. Okay? I highly recommend going to Antarctica. It's one of the most beautiful places on Earth. I happened to be there on a full moon day, which is one of the most beautiful things I ever saw in my life. Okay, the thing that happened though is that this happened in 85, and very quickly, by 1988, we knew exactly what caused it. My colleague Susan Solomon proposed this is due to CFCs. There are a bunch of measurements that are carried out, and it was actually fascinating to do this. And the smoking gun kind of was the picture where the ozone was measured from our lab in Boulder, Colorado, and CLO by scientists in Harvard. And it very clearly showed this is exactly how it happens. The goal, and at the same time, the global ozone layer depletion was also detected in 1980s. Not in 2050, but in 1980s. There's an ozone depletion, and it's predicted. Now what? That is when it became a societal issue. And it caught the imagination of people, and it made the Time magazine. I know some of you youngsters might even know what Time magazine is. This used to be more powerful than Facebook in those days. Okay. People actually read in those days printed paper. Okay, so here we are. Here's the ozone layer depletion was observed, projected. Ozone depletion it led to a societal issue, and something had to be done. By mid-1980s then, the consciousness was ozone hole has appeared, it's massive, it's being depleted, caused by humans, and then what? That is what led to the Vienna Convention of 1985 and the Montreal Protocol of 1987. Those are two very important dates. For my life, actually, they're important because my son was born in 85 and my daughter was born in 87. It all depends on how you look at it. This, incidentally, is a nice paper by Tina, if you want to take a look at it. Now, at that point, the world had a choice. What are you going to do about it? What this shows is the amount of ozone depleting substances. For those of you who are aficionados, this is something called equivalent chlorine. I'm not going to tell you about it. It was going up, and socioeconomic models predict that this is what it's going to grow to be. At that point, the world could just decide to adapt to the ozone layer change. So you could cover yourself so that you're not affected by the ozone, and that's an adaptation strategy. But amazingly, the world actually decided to mitigate climate change and get rid of CFCs. It was a big step in humanity. Okay? So the world actually opted to mitigate, and the Montreal Protocol was the result of it. But you'll see that Montreal Protocol just didn't happen like that. But the key point, though, was that science was a key ingredient in this decision making. First, the discovery, the scientific understanding, scientific accessibility, and most importantly, let's not forget that this science had to be taken to the policymakers so that they could understand it. This is the role that developed. It's called the assessments, where you actually assess the scientific information. Based on peer-reviewed literature, there's a whole host of things you can think about as to how this works. And I need to kind of speed up a little bit. So, science foreshadowed policy, and the Montreal Protocol just kind of slowed it down a little bit. It didn't completely eliminate CFCs. Then came other bad news and other things that happened, and our scientific understanding improved. And over the course of another 10 years, essentially, the world decided to phase out all these chemicals completely, and that's what we are. Thus, advancement in science was the key to the impetus in policy. So this is the kind of roadmap for how to deal with it. CFCs, you get rid of it, get something else that is a little bit better, and then finally something even better, and all of these things went on science. Now, let me ask you a question. How many of you actually knew that your refrigerators that you grew up with as kids are different than the refrigerators of today? And how much monetary or inconvenience did it cause? You didn't even notice it, did you? You hardly knew that it even happened. That, folks, is a way to make scientific policy that's really easy to adapt and do. Okay, so I'm going to just tell you about all these things I just told you. Unnecessary uses went away. There's a quick relief. There's a whole issue of short-lived climate forces, pollutants. And then it allowed for existing equipment, ozone-friendlier things. It allowed not-in-kind technologies, and then HFCs came about. Now, I'm not going to spend too much time on this other than to just say the key thing from my perspective was this whole issue was done in a way you took baby steps, one little step at a time, so that you could go back if necessary, but also make progress as you went along. There's a very important consideration, in my opinion, outcome that led to it. But let me just spend a minute. What if we hadn't had a Montreal Protocol? What would have happened? This is, as I showed you, is what is projected. The middle panel tells you what's actually happening, and the other panel tells you what would have happened if you had no Montreal Protocol. I want you to focus that in 2020, which is already passed, the amount of UV radiation in Orléans would have been about 40% higher. The UV depletion, ozone depletion would have been about 40% above Orléans, which means the UV would have been doubled or increased by a factor of 2.5. So the amount of time you could spend in the sun would have been very, very tiny. You would all be waiting for cloudy days and go to Paris or something, I don't know. Okay. The point, though, is it really prevented disasters. There's other major things it did. It actually prevented depletion of ozone over the tropics that would have caused even a bigger issue. And lastly, by this time, the ozone depleting substances would have been the largest climate forcing agents, not CO2. That's how much of an effect it would have had. And it was averted because of that. Okay, so Montreal Protocol is a success, blah, blah, blah. You can see it started decreasing, things are getting better. But are we done? What else can be done with the Montreal Protocol? I just want to mention that, as I said, these same chemicals that are ozone depleting substances are also very powerful climate forcing agents. Okay, so there's the two phases of these ODSs, and there's things done about it. The simplest way I can explain it is the Montreal Protocol, by its actions, did 5 times more than the Kyoto Protocol did for climate. Okay? This was not the goal of Montreal Protocol. The Montreal Protocol was done to save the ozone layer, but it did more to prevent climate change than the Kyoto Protocol. Okay. Now we are in the situation we are trying to manage and deal with this kind of stuff. This is what you would call an accountability phase, because it is not just sufficient to know that you took these actions, but you want to make sure the actions you took led to the results you wanted. So otherwise, you go back and change things. That's what has been done during this entire process. That led to the whole issue of HFCs. Incidentally, this is what's in your refrigerator, your air conditioners quite often. You can change it. You should. You could use hydrocarbons. That is going back in a circle. But anyway, this whole thing of Montreal Protocol Act actually broke the climate efforts in a way and led to the HFCs, and HFCs needed to be phased out. And that led to, I'm going to skip this because it's not, I'll be happy to come back and tell you about it. That led to the Kigali Amendment. This is the amendment that happened in 2016, where the countries agreed for the first time that the Montreal Protocol, originally designed to deal with ozone layer depletion, is also going to take on this bit and deal with climate change. Okay? So if you think back on it, in my lifetime, 45 years ago, the damage of the ozone depleting substances were first predicted. 35 years ago, ozone hole was discovered, roughly. Today, ozone is showing indications of recovery. But here's the catch. Even when you stop taking these actions, that doesn't mean you're going to get the results. The legacy of these emissions is going to be with us for quite a while. And that's because of two things. When you put things like these ODSs into the atmosphere, it doesn't go away. It's just like CO2. It sticks around for a long time. Second, the effect it has caused also stays. It stays not only in the atmosphere, it stays in the people. If you were exposed to harsh UV radiation as a child, it's going to affect you 30, 40 years later. So that's this other aspect one has to think about. Okay, now the question is the Montreal Protocol done? Is it finished? We think it's not. Here is a few things that one might think about and Montreal Protocol can do, that is to toughen compliance, eliminate feedstocks. These things probably won't mean anything to you unless I went into it. I just want to point out a few things that you might know. Nitrous oxide, the game you're supposed to play that makes you laugh in this building, supposedly, that is another ozone depleting gas that's being emitted. that could be controlled, and it's also a very important climate gas. And the thing that we haven't done very well is to make sure that the actions we have taken are being followed. In other words, you can have a policy, but if you don't implement the policy, it doesn't do much. So you got to make sure the atmosphere's things are working as predicted, and then we think Kigali could do something more. Now, I want to end with a very brief thing about what did we learn from the Montreal Protocol? Why is it Montreal Protocol so successful? Incidentally, the Montreal Protocol is the only treaty that has been ratified by every country on earth, okay? Including North Korea, including South Sudan after it became a country. I have no idea what's going to happen when some of the geographical changes occur, but the point though, it is a universally ratified treaty, and so it must be there is something that's right about it that makes it work. It provided, in my opinion, a way forward that is easy to do. You don't try to do everything in one big step. It's hard to swallow. Try to do it in steps that you can kind of bite into. Don't try to get rid of CO2 all at once, which you can't do anyway. You can do it in steps. It also provides a viable option for the society, industry, and the government. How do you actually do this? Most importantly, it bought some time in the beginning by getting rid of things that could be removed very quickly. I'll come to that in a second. There's a whole issue of this concept of atmospheric lifetime and what it does. I'll be happy to talk about it if there's time. And this is an important way of doing adaptive management. So I suggest that the lessons of climate change mitigation and adaptation lessons for them can be learned from the Montreal Protocol. So if you think along those lines, one of the things that comes up very quickly is this methane for a climate forcing agent. Okay, we just published something called a global methane assessment. That was the basis for European Union and the US to promise certain reductions by reducing methane. And this is what it's all about. Because methane lives in the atmosphere for only about 10 years, if you reduce methane now, it helps you now and in the future. It also helps global air quality. So you're actually trying to look for win-win options. So methane reduction can help mitigate climate change and improve human health and agriculture. And there are some numbers as to what can be done. If any of you are really curious what you can do about it, I'll be more than happy to tell you. So let me just kind of summarize very briefly. In my opinion, the ozone layer depletion issue from a scientific perspective, from a policy perspective, it's a triumph. The postulations led to action within decades, in my lifetime. Montreal Protocol is one of the most successful international agreements. So there are things you can learn about how to do other things in what's called the ozone regime, if you're thinking about from policy perspectives. Montreal Protocol has lessons for other environmental issues in a whole host of ways that we can talk about. I just want to end by my favorite cartoon by Gary Larson, that how, the ozone layer is shielding the rest of the solar system from the Earth's harmful radiation. But the most important thing, though, is think about this. The society did something about a layer they cannot see, the ozone they cannot see or feel, and actually took action to protect it, and protect it for now and in the future. So to me, that's a very hopeful sign. Thank you for your attention.